study that brought us to a new definition of the sphere of influence of the Earth. And this was done in collaboration with Irene Cavallari, Giulio Babu, and Giovanni Grassi. I'll start with a brief introduction on the concept of the sphere of influence. I will introduce the Jacobi constant and the Tisserand parameter, which will be both very useful for the rest of the talk. I will describe the computational method that we use to define the sphere of influence, and I will present some results, and finally I will introduce some possible future ideas. So the concept of the sphere of influence of a planet was first introduced by Laplace in 1805, and he was studying how the orbit of a comet is perturbed by the action of a planet. And what he did was to propose what he called a sphere of activity of the planet, inside which we could just think about the presence of the planet and forget about the sun, while outside the sphere of influence, we would only consider the attraction of the sun on the small body. It turned out that this idea could be useful in different contexts, for example, in monitoring and the design of interplanetary trajectories. So there have been various definitions of the radius of the sphere of influence. The first one was given by Laplace himself, and another well-known is, of course, that given by Hill. And in both cases, the radius of the sphere of influence would depend on the distance between the planet and the sun, which is denoted by rho, and on the mass ratio between the planet and the sun raised to some power. And also another less known definition is that given by Chebotarev, and again, we have the dependence on the same two quantities. However, more recent studies have proposed that actually the sphere of influence of the planet should depend also on the small body having the encounter with the planet, not just on the planet itself. So this is basically where we start from. We wanted to find the most suitable definition of the sphere of influence to be applied to the Sun-Earth problem, and in particular, we wanted this to be the best sphere of influence to be applied to the Planetary approximation. So the idea of the Planetary method is to split the orbit of the small body in 3 different sections. So outside the sphere of influence, before the encounter, so in this region here, we would have just a 2-body problem with the sun and the small body, and so the small body would just be on an elliptic Clarion orbit around the sun. Then once we reach the sphere of influence, we switch the center of gravity. Now the small body is only attracted by the planet, and so inside the sphere of influence, we have a hyperbolic Clarion orbit of the small body around the Earth. And then once we leave the sphere of influence, we're back to the 2-body problem, sun, small body, and the orbit is again an elliptic orbit, which is different from the one we had previous before the encounter. And for the study, as I said, we decided to focus on the sphere of influence of the Earth, and in particular, we restricted to the planar phase. All right, so we take a synodic barycentric reference frame. So we have the sun and the Earth in fixed positions on the x-axis, and the small body, which I'll call an asteroid, will move around. And here we denote by R the distance of the asteroid from the sun, and by D the distance of the asteroid from the Earth. And the Hamiltonian function of the circular restricted free-body problem is written here. And we have the Jacobi constant, which is, of course, an integral of motion, and which is written here in terms of the heliocentric orbital elements of the small body, in terms of the distances D and R, and the angle alpha, which is the angle between the asteroid and the Earth, as you can see in the picture. So if we consider this first 2 terms here, this is actually what is called the Tisserand parameter. And the difference between the Tisserand parameter and the Jacobi constant is then just given by the other 2 terms. And what you can see from this difference is that this becomes relevant when the distance d between the asteroid and the Earth is small, so that the ratio mu over d becomes relevant. So what we see from here is that the Tisserand parameter is actually very useful in studying close encounters, and we have that its value follows a general behavior, which is described here. So we have that before the encounter, the Tisserand parameter has an almost constant value. Then it decreases once we get closer and closer to the planet, and it increases again. And then after the encounter, we have a constant value again, which is very close to the pre-encounter one. So what we were really interested in was to find a distance from the Earth at which we could be sure that the Tisserand parameter is almost constant. And this would depend on the value of the Jacobi constant C of the specific small body that we're considering. So what we did was we took the time derivative of the Tisserand parameter, and we asked that it's less or equal to some small quantity epsilon. And we defined dc as the smallest positive distance for which this inequality is satisfied. And what we found was that the distance dc is a decreasing function of the Jacobi constant. So in this picture here, we have the Jacobi constant on the x-axis and the distance dc on the y-axis units. And as you can see, it's decreasing, and this was done by setting a value for epsilon 5 times 10 to the minus 4. So we took this distance dc and we used it to define the initial conditions that we will apply in our method to. So in the synodic Large-centered reference frame, we take a circle of radius d0 centered in the Earth, where d0 is a distance that is slightly greater than dc. And so the initial positions of the asteroid will be on this circle of radius d0, and this makes sure that when we start the initial conditions of the asteroid are such that the Tisserand parameter at the beginning is almost constant. And as far as the velocity goes, we know from the expression of the Jacobi constant that actually the modulo of the velocity is completely determined once the initial position and value of the Jacobi constant are fixed. So the only thing that we had to define was the possible directions of the velocity. And we decided to take as initial velocities those that point towards the inside of the circle of radius d0. And this is because we wanted to have initial conditions that got closer to the Earth. So at least in the beginning, this is what happens. So in the end, we have that the initial conditions will be defined by 3 parameters: the value of the Jacobi constant and 2 angles, beta and delta, where beta gives us the initial position and delta gives us the direction of the initial velocity. So for each initial condition, we then computed the free-body orbit using the circular restricted free-body propagation, and we went from a time t0, initial time, to a final time t1, which is defined as the time when the distance between the Earth and the asteroid becomes again the value t0 from which we started from. And this was because, again, we also wanted the propagation to end when the Tisserand parameter is almost constant. Because the distance between the asteroid and the Earth can become quite small during propagation, we also use the Levi-Civita regularized variables to handle the free-body propagation. So then we wanted to find a way to define the best sphere of influence, so we implemented an optimization process. We define a target function f, which is made of 3 separate parts. The first component gives us a measure of the maximum distance between the free-body orbit and the Cauchy orbit that we get by selecting a specific radius, so that's called sphere of influence. The second term gives us distance between the Cauchy and the free-body orbit at final time t1, while the last term gives us the distance between the 2 orbits at the time of mean distance from the Earth. So for each initial condition, we then took an appropriate interval of possible radius of the sphere of influence that we wanted to test. We took the uniform sampling of this interval and computed the Cauchy orbit associated to that value of the radius of the sphere of influence. And then we evaluated the value of the target function for each Cauchy orbit, and we chose d star as the value that minimized the value of the target function. In doing this, we had to throw out a few conditions, also depending on the value of c, and these were conditions for which the geocentric distance of the three-body orbit has multiple minima, and to these initial conditions, we can apply this method. So after determining value D star, which gives us the best approximation to the three-body orbit using a attached conic orbit, we also wanted to see the result that we would get if we would just consider a purely heliocentric elliptic orbit. So we computed the heliocentric elliptic orbit from time t0 to t1, and we computed the value of the target function in this case. And so in the end, the selected radius of the sphere of influence will be 0 if f of kh is less or equal to f of d star, which basically means that the best approximation to the three-body orbit is given by a purely heliocentric orbit. And instead, in all other cases, we select a radius of the sphere of influence, the value star that we got on the optimization process. So we applied this procedure to a bunch of different initial conditions by varying the values of the Jacobi constant and of the angle theta and delta. But of course, these don't cover every possible initial conditions that we could take. So for any conditions C, beta, and delta, this that is inside some volume P. We propose the application of a trilinear interpolation method. And what this would mean is that if we take the three planes that are parallel to the faces of P and that go through the points C, beta, and delta, these three planes split P into 8 smaller parts. And then to compute the value of the interpolated radius of the sphere of influence in points C, beta, and delta, we would take the value that we already have computed in each of the 8 nodes, and we would multiply this by the volume of the smaller part that is diagonally opposite to the outer reference ring. We take the sum of all these products and we divide it by the complete total volume of P, and this gives us the interpolated radius of the sphere of influence in this point here. So I will now present a few results, and in all these slides, I will use a representation on the beta delta plane with 2 angles to define the initial conditions, and then the quantity that I'm plotting in each case is described with a color scale, and the value of the quantity will increase going from blue to yellow. So in this first picture here, we have represented the value of the selected radius of the sphere of influence with our method. And we've used here a value of the Jacobi constant equal to C 2.97. So the large dark region in here and then above here is where our method selects a value of the sphere of influence equal to 0. So this is the region where the best approximation is given by a purely heliocentric function. And instead, in this central region here, with all the different colors, this is where we actually have a non-zero sphere of influence. Now, if we compare these 2 pictures, on the right, instead, I've plotted the minimum to centric distance that we reach with the 3-body propagation. And the white dashed line is initial conditions in the beta delta plane that lead to collisions with the Earth, and the minimum distance then increases as we move away from the collision curve in either direction. So what we can see by comparing the 2 pictures is that the region where our method selects a radius of the sphere of influence that is non-zero is exactly the region surrounding the collision curve here. And this makes sense because this is where we get closer here. So this was good. Here I've plotted instead the value of the target function with our selected radius of the sphere of influence. So this is basically the lowest error that we can get. And here you can see that the values, the errors are generally quite low. The only region where it gets really high is for points that are on the collision curve or very close to it. Finally, not finally, but yeah, so as you can probably tell from the target function that we chose to use, we were interested in computing a quantified approximation that would stay quite close to the 3-body orbit throughout the time span that we're considering, and that's the reason why we took that first term in the target function. But we were also interested in making sure that we were close to the free body orbit into specific times, and those are at the end of the propagation. So we wanted that the final condition that we get with our approximation is actually close to the free body orbit. And we also wanted to make sure that the difference at the point of minimum distance from Earth was quite accurate. So here I studied the relative errors on the post-encounter semi-major axis and eccentricity, comparing the free body orbit and the Pashaponic values. And what we can see here is that the errors are really low. This is a zoom on the specific region. Doesn't like that the errors are very low throughout the plane. And the only points where it gets quite high is for a few points here and here, which again are on the collision curve or very close to it. And these same pictures, we definitely basically have the same pictures also if we check the relative errors on the eccentricity and geocentric distance at the minimum distance, so rapid parity. So we can see that generally the Pashaponic approximation that we select is close to the free body orbit in these two specific times. And so then we also wanted to check the results of the interpolation method that we proposed. And to do this, we selected a smaller region in the beta delta plane, and we took a finer grid of initial conditions for which we didn't already have the computed value of the radius of the sphere of influence. And for each point of this finer grid, we compute the interpolated radius of the sphere of influence. And then we take the difference between the value of the target function with the interpolated radius and the value of the target function with the field radius here and with the Laplace radius here. As you can see, this the values in this region are always negative. This means that even with an interpolation, even with the interpolated radius, the value, the error that we would get with our method is still lower than the one we would get by using field radius or Laplace radius. This was good. However, I should say that this region in the beta delta plane is taken where in a region where we are still quite close to the collision curve, so where the minimum geocentric distance is still quite low. However, if we were to move towards more outer regions, so where the minimum geocentric distance is higher, the interpolation method doesn't work as well. So that should be studied more thoroughly. And so finally, what we would like to do is to extend this procedure to the three-dimensional case. This can be done, but we would need to improve the computational efficiency and also the storage of data because of the high number of initial conditions that we would need to consider, especially if we want to then apply the interpolation method. We would also like to apply this to other solar system planets. And finally, there are still some things that need to be understood. For example, we would like to investigate better those points for which we have higher errors closer to collisions, or those for which the method cannot be applied at all. And that's it. I think.